Okay, let's get started. Thanks everybody for coming. It's my pleasure to introduce Steve Parman, today's speaker. Steve and I have been colleagues for several decades. Earlier in our careers, we were working on similar problems related to ultramafic magnetism. In fact, we spent 2 weeks in Western Australia collecting komatiites once, which is a lot of fun. Steve got his PhD with Tim Grove at MIT in around 2000 or so, I suppose. Went on to a postdoc at MIT and Harvard. Mm-hmm. And then was a lecturer, went on from there to become a lecturer at Durham University in the UK. And I think after about 3 years of not seeing the sun, decided to come back to the US and has been a professor at Brown ever since. Today, Steve's going to tell us about tracing volatile recycling into the mantle with noble gases.
All right. Well, thank you for having me. Yeah, I remember that trip to Pilbara in Australia started with picking up Mike at the airport. And you remember this in the taxi? And this taxi driver proceeds over 20 minutes to tell Mike every animal that was going to kill him. Every spider, every plant. I think by the end of that taxi ride, Mike was not totally sure about what we were about to embark on. But we didn't die. Okay, so yeah, I've been looking at noble gases and how they behave in minerals for many years. And so this is kind of where we've gotten to now, but involves a number of people, including Colin Jackson, who is here. You'll see some of his work, and my current student, Jack Krantz, who's kind of continued on in following on Colin's work. All right, so this is an old picture from Stan Hart, a little pixelated, but I like it. It kind of shows all the things that I'm interested in, and I think a lot of people in this room, the Deep Carbon Observatory, about how do we cycle elements in and out of the mantle, and in particular, if we're thinking about volatiles. Clearly, subduction plays a big part in bringing volatiles into the mantle. Questions about how deep do they get subducted? Do they go all the way down to the core? Do they get stuck in the mid-mantle? How do they return? How much come out shallow in subduction zones? How much go all the way to the core mantle boundary and have to come out in plumes? There's a lot of complexity, and we'd like to be able to trace how volatiles move through the mantle. Now, the major volatiles like water, CO2, sulfur, that have kind of chemical and physical impacts on the mantle, unfortunately are fairly isotope poor. And so it's a little difficult to do some of the kind of tracing that we do. Typically with isotopes, those isotopes can get fractionated pretty easily during degassing. And so there's just a kind of a fundamental problem. If you wanted to trace, let's say, water through the mantle, you don't have a lot to work with. And that leads us to the noble gases. And I kind of want to sell you that the noble gases are kind of like the rare earth elements for volatiles. The rare earth elements have been extremely useful in understanding all sorts of processes within the mantle because they have they have the same valence state, but they have a varying atomic radii. And this lets us essentially probe mineral structures, see fractionations that we can identify with one mineral or another. And the noble gases have this property. So here they are, and here they're radii, and it's a fairly smooth increase in radius. And the hope is that we should be able to see minerals fractionating them from one another and use that to trace the processes that are going on in the mantle. In addition to that, they're isotope rich. In some sense, when my students who are much more fluent in xenonology than I am start talking about all the different isotope anomalies, sometimes I feel it's a little too rich, but we've got, just in xenon, we've got 4 stable isotopes. We have 1 short-lived radiogenic system, 129 from the decay of iodine, and then 4 physiogenic isotopes. And you basically have a nice toolbox. I'm not going to go through all the details of these, but you have a nice toolbox if you want to trace not only kind of fingerprinting sources with stable isotopes, but even getting into timing of when various inputs and outputs may have occurred. And a really great example of this is someone familiar to Rita Parai published a really nice paper in 2015 using the kind of suite of xenon isotopes. And basically, you can fingerprint 4 components that have distinct isotope signatures. And for our purposes, the only one you need to focus here is the blue, which is the recycled atmosphere that we see in the mantle. So the atmosphere is a distinctive xenon isotope composition. And you can compare that to the mantle. And basically, she did a multi-linear regression to pull out how much of this recycled air is in the sources of mid-ocean ridge basalts and plumes. And what had been hinted at before by people like Chris Ballantyne was that much of the xenon that is in the mantle, whether it's the morb source or the plume source, was put there by recycling, by subduction. And if you think about that, it means you have subducted xenon all the way down to potentially the core mantle boundary. And so the essential question that we've been looking at for the last few years, starting with Colin, is how can you do that? What is the vehicle that can hold on to xenon all the way down into the mantle? And yeah, so the picture that has emerged from these isotopic studies, not just of xenon, but the other isotopes, is that some noble gases seem to be recycled and others not. In particular, helium and neon, it looks like there's very limited evidence for recycling of those back into the mantle. And that's likely due, because they're very low concentration in air in seawater. Argon is ambiguous. Argon, the stable isotopes in the atmosphere and the mantle are the same. And so you can look at that and say, argon's been completely overprinted in the mantle, so it's 100% recycled. Or you can think, well, maybe they just have a common origin. So unfortunately, if you have no isotopic difference, you can't do too much with that. And the ones we're going to concern ourselves with today are krypton and xenon. As I showed you from Rita's work, you can also do that with krypton. And they're not entirely overprinted, but they are dominated by subducted components. And what I want to try to do today is show you that we're starting to be able to tease apart what those subducted components are by understanding the behavior of noble gases in minerals. And then even more fantastically or surprisingly, in 2017, just a few years ago, a paper was published by Bernard Marti's group looking at the xenon composition of air. This is modern air. Here's age. And this is 129 xenon, short-lived isotope. So it should have died right up front in Earth's history. And the expectation, this is solar wind, was that the evolution curve should look like kind of a hockey stick, and that for most of Earth's history, it should have been modern air. These are analysis of fluid inclusions and cherts from Archean samples, and the surprise was they're kind of intermediate between solar wind and air. And so it looks like some process, which we're not really sure what it is, was continuing to fractionate these isotopes over a couple billion years of history. For our purposes, what's really interesting about this is Rita's work, where she showed that the xenon was mostly subducted air. She used modern air, because she was doing that before this was known. And the mantle looks like modern air. If she uses this Archean air, it doesn't look like modern mantle. And so this gives us some idea. It's not a very accurate timer, but it definitely tells us that most of the xenon that's in the mantle now has been subducted just in the last couple billion years. And if you want to kind of squint and say, well, maybe that means subduction turned on after the xenon evolution, and that's, I think Rita kind of points in that direction. But anyway, so the evolution of xenon in the atmosphere, kind of unexpected evolution that we see, gives us some ability to time when these inputs happened. Right, that's what it is. Okay, so how are noble gases subducted? What's the vehicle? Is it in pore spaces? Is it on grain boundaries? Is it dissolved in the minerals? And this is kind of where we come in. So Colin's first project when he was a grad student was to measure noble gas solubility here, helium, in olivine, clinopyroxene, OPX, but now mantle minerals. And the general answer is it's very low. You can't put a lot of noble gases into your typical mantle minerals. Interestingly, they're all kind of similarly low. It doesn't really seem to care what the structure is. And so if we're trying to subduct noble gases, we're not retaining it in like the depleted Hartsbergite residues or in unaltered basalt. They should all be pretty degassed. And this was kind of the viewpoint, kind of canonical viewpoint of minerals don't hold on to noble gases, so we don't subduct noble gases. So if you look at models of noble gas, kind of isotopes up until 10, 15 years ago, in general, you had outputs from the mantle to the atmosphere, but you didn't have any return signal. You know, if you look at like a water cycling model or CO2, there's outputs and then there's inputs back in. Those inputs didn't exist in the noble gas models. And so then Colin, being kind of the creative guy he was, we were working on different things, and he decided to look at amphiboles. And I thought this is a really cool result. So these different symbols are different amphiboles from tremolite, pargasite, actinolite, richterite. And this is the concentration of helium in those amphiboles in ppm per kilobar of helium. And what you see, well, you can't, I don't have olivine. If I was going to plot those olivines and OPXs here, they'd be at 0. They're like 3 orders of magnitude lower. So the first result was amphiboles can suck up huge amounts of noble gases relative to kind of normal mantle minerals. And this gives us an idea of why, because amphiboles have SiO4 rings in them. And what I mean by that, here's the amphibole structure, and here you can see this ring of tetrahedra, and there are actually 2 stacked on top of each other, and in amphiboles they can be filled or not filled. And what he found, and so this is the amount, the density of vacant rings. So these are filled, kind of stuffed, the rings are stuffed by sodium or potassium, and then these are mostly vacant. And you can see as the rings become more and more unoccupied, the noble gases fill in. So not only do we see that the solubility is high, we think we know where they are. They're in these ring structures. And again, being the kind of curious person that he is, Colin said, well, lots of minerals have rings. Let's look at different types of minerals. And he also did helium, neon, and argon. And here's that amphibole data. He added neon. You can see maybe it's fractionating helium from neon. So this is kind of what we're looking for. Can we see minerals fractionating noble gases? If they do, then we can start to use that to trace them. Here's antigerite and chlorite, kind of order of magnitude lower solubility, and then beryl and cordierite, screamingly high. These are the highest noble gas solubilities in minerals that we've measured. And we have the mineralogist from the Smithsonian. What's the difference in the arrangement of the silicon rings in these different minerals? Yeah, so these are single rings. This is a double ring, and then this is an infinite stack of rings. And so it looks like the more you stack the rings on top of each other, the higher the solubility. And we're not exactly sure what's going on here, but our hypothesis is it's all about polarizability, right? So how are we getting noble gases to bond into a mineral structure? Well, it has no net charge, but you can polarize it so that one side of it has a charge. And then, so the most anisotropic site, the site that has the kind of the least homogeneous electrical field, should be the one that polarizes the noble gases the most. And these rings are those sites because you have electrons around the kind of the equator, but there's nothing north and south. And so we think the more you stack them, almost the more anisotropic the site gets, and maybe it's polarizing the atoms more and more. If there's an ab initio modeler out there that wants to take on amphibole, I would love to see a model of that. The few ab initio models or in molecular dynamics, people I've talked to about doing this, when I showed them amphibole, they were like, no, I don't want to do it. Yeah, it seems like it's complex. I don't know anything about it. But the suspicion is that this is about increasing polarizability, or the anisotropy in the site. The other thing that is kind of exciting about this is now we're seeing, it looks like we're getting different fractionations in different minerals. And again, using the analogy of rare earth elements, if we have this, it can be extremely useful. Now, if we look at subduction zone, this is a figure from Schmidt and Pauly, and kind of phase diagram. Here's amphibole, serpentine, phenjite. These are hydrous phases in the slab. Many of these have ring structures in them. And so, once we kind of made this connection that these rings are holding on to the noble gases, and you look at the possibility of slabs subducting noble gases, it looks pretty good. But as I said before, really it's about krypton and xenon, and Colin had worked on helium, neon, and argon, and so really the obvious next step was to look at krypton and xenon in these minerals. And the ones where I'm going to show you data for is serpentine, and then we have some natural samples that people have analyzed from amphibolite. So just a little bit about the experiment. Where's the clock? Not doing too bad. We take as clean antigerite as we can get, and there's this Japanese antigerite. It's not perfectly clean, but there are clean spots in it. These are magnetites. There's fluid inclusions. It's also multimineralic. It's not a single crystal of antigerite. So that's where we're not doing partitioning into serpentine. We're doing it into serpentinite. And so there's grain boundaries in here. There's all sorts of things we have to deal with. But because we're going to do laser analysis, we can analyze cleaner spots and dirtier spots and look at their differences, and that helps us tease apart where the noble gases are. But we basically expose them to noble gas atmospheres. Because krypton and xenon are so expensive, we kind of do them in two shots. We have a helium, neon, argon bottle, and we have an argon, krypton, xenon bottle. Up to a kilobar, 350 degrees, up to 180 hours. We basically soak them in noble gases and see what their solubility limits are. This is the laser at the Open University that we use. There's the laser, you zap it, the gases get scrubbed here, and you can also introduce standards, and then you put them through the mass spec. One of the interesting things about this is because your standard is a gas, not another solid standard, the only way you get concentrations is by measuring the size of the hole that you've made. In typical kind of laser ablation trace element analysis, you analyze a standard, you analyze your sample, and you assume the holes are kind of the same geometry. Here we have to measure it, and actually this is the largest source of error in the analyses, because it turns out when you're digging very shallow holes, being able to measure exactly the depth and if there's any non-flatness to the hole, getting its exact volume is an interesting little challenge. This is a white light interferometer, and then we kind of model this surface actually using software that the cratering people have for looking at volumes of craters on the moon. We borrowed their software to do it. And so this is the data this is Jack's, my graduate student Jack Krantz, his experiments. Sorry, these letters are a little small, but helium, neon, argon, krypton, xenon. the Henry's constants. We're not going to worry too much about helium. It often seems to be playing kind of its own game. So we're just going to really focus on argon, krypton, and xenon. And you can see a rise in solubility and a huge spread. So here for argon, there's a 2 orders of magnitude spread, and it kind of dies down a little bit. But even at xenon, we have an order of magnitude. And these spots are the ones that are in the dirtier, either a magnetite grain or a fluid inclusion rich area. And so we believe that a lot of this spread is caused by those inclusions. And as in many solubility partitioning studies, the lowest values win. Now, when we start to get really low, we start to get close to the detection limits of the machine. So, one option is to say that this is the solubility, but we're just not sure about the errors on that. So this is the solubility line we've taken as our kind of best fit values for the solubilities. And you can see you're going to fractionate xenon from krypton from argon, and serpentines are going to end up with high xenon to argon and high krypton to argon ratios relative to whatever they partitioned with. All right, so one thing we can do with this is just take these solubilities and make a model of how much noble gases we could stuff in to serpentinite. So here's a subducting slab, there's a serpentinite. This is the altered oceanic crust, and then this is, not to scale, the sediments. These are kind of our 3 components where we're going to think about where we can stuff noble gases. And with our serpentinite data, we can take a stab at estimating how much noble gases are here. From natural samples, we can, of sediments, altered oceanic crust, and actually there's analysis of natural altered oceanic mantle. We can have estimates of the sediment and the amphibole and take a guess at how the flux of noble gas is going down. And that's what these are. This is the argon mass balance. So this is argon 36, basically a stable isotope proxy. And then this is the thickness of the layer. You have varying thickness of sediments that we can model. Oceanic crust, obviously much more limited. Thickness variations. And then this is the estimate of noble gas concentrations from our experiments, varying with thickness of the amount of serpentinite that you formed. And there is some question about how deep serpentinization goes. There's been some recent papers that suggest 30 kilometers is not an unreasonable value. And then from the analysis of natural samples, the concentrations are kind of an order of magnitude lower. So this is kind of our range for potential amounts of noble gases of argon in the serpentinite. And you can see for argon, really the serpentinite's going to dominate the flux of argon back into the mantle. If sediment's kind of more reasonable, a few kilometers, it's going to be almost negligible. If you have not too much, only 10 to 15 kilometers of hydration of the mantle, maybe the oceanic crust and the serpentinization or the serpentinite could have subequal values. But if we're really talking about 20 to 30 kilometers of serpentinization, we think most of the argon will be in the serpentinite. For krypton, now we see a little bit bigger spread between the experiments and the natural samples, but now the sediments are starting to creep up and become a larger component. And in particular for xenon, sediments are pretty xenon rich. And if you do have kind of on this order of 10 to 15 kilometers of serpentinization, potentially sediments could be about an equal flux of xenon into the mantle as a serpentinite, with altered oceanic crust kind of being a minor component. All right, so now we kind of have an idea of what those fluxes are. How do they compare to how much noble gases are in the mantle? So here are the fluxes we calculate for kind of average values of thickness of sediment, crust, and hydrated mantle. And if you take those values, let's say for I don't know that, all right, that's a mistake. if you take these values, the noble gases would be, I see, that should be over there. With these values, you would overprint the depleted mantle completely with seawater or air isotopic composition for argon in 100 million years, krypton 67 million years, and xenon something like 30 million years. And because we know that krypton and xenon are not completely overprinted, we know this didn't happen. And so what must be happening is that the slab, as it's going down, is losing most of its noble gases. If we do the whole mantle, it's a larger reservoir, including the lower mantle, which has higher concentrations of gas. These ages get a bit longer, but still shorter than we think subduction has been going on. And because argon isotopes in the atmosphere and the mantle are the same, we can think of a steady state model where basically the amount of argon going in is the same as it's coming out. And if you do that, you come up with a number of something like 99% of the argon that we think is going down in subduction zones can't reach the mantle. It must be coming out shallow, and only 1% or less, it could be 0.1%, even 0.1% is what's getting subducted deeper into the mantle. But importantly, because the solubility of noble gases are so high in these ring-bearing minerals, even this 1% is enough to have a large effect on the isotopic composition of the mantle. So in some sense, the older models were right. Subduction is a big barrier to subducting noble gases into the mantle. Not a lot make it down. Most of it, the large majority of it, does come out, we think, in the subduction zone, but the amount that survives is still enough to have a big effect on the mantle. So now we can use isotopes to say, okay, not only are they going down, but can we trace where they're going and what's bringing them down? So for the next few slides, we're going to focus on this plot again. Sorry, it's a little small. This is xenon to argon. It's 130 xenon to 36 argon, stable isotopes. And this is 84 krypton to 36 argon, again, just krypton to argon. And remember when I showed the partitioning of serpentinite, xenon had the highest solubility, followed by krypton, followed by argon. So what we expect from serpentinite is it's going to increase these ratios. So here's just some background analysis of natural samples. This is where air is. This is where seawater is. And then here's where mid-ocean ridge basalts are, and presumably the mid-ocean ridge basalt mantle, the depleted mantle. And the important thing to note here is they're not the same. You can't make the morb source, simply by air and seawater. There has to be some other component. And this is where you get the idea that you have to have subducted something. Chris Ballantyne and others have suggested sediments. So all these other dots are different analyses of sediments, and they kind of get you in the right direction, but they are kind of all over the place. And so depending on what sediment you choose, you can make morb, but not entirely clear that it's going to be the solution. And we also, So here's our serpentinite fractionation line. This is, again, that same xenon, argon, krypton, argon plot. So this is what we expect the serpentinite to look like that's being subducted. And we think it's fractionating, it's equilibrating with seawater. So that's why we're doing it from seawater, not from air. And it goes pretty close to mid-ocean ridge basalts. And so you could make morb, the xenon, krypton, and argon isotopes, stable isotopes, and the morb source is consistent with them predominantly being put there by subduction of serpentinite. We can look at other places like Iceland, heads off in a very different direction, actually quite consistent with sediment. So this is where this arrow is pointing towards sediment, and that's actually consistent with other isotopes, strontium, neodymium, lead, that have been analyzed in Iceland, that I believe have suggested some sediment input, whereas Hawaii heads to much more fractionated xenon-argon ratios, pretty similar to morb and kind of consistent with maybe these noble gases being subducted by serpentinite into the Hawaiian source as well. Now this is the same plot, but the scale has changed dramatically. Here's air, seawater, and morb. And what I'm showing here in this dark field, these are high mu basalts. Now these are, for the non-isotope aficionados, this is a flavor of mantle that, largely based on the lead isotopes, is thought to be heavily influenced by the subduction of altered oceanic crust. And you can see, like, uniquely amongst all the mantle sources, the high mu plumes in their mantle source have extremely fractionated heavy noble gases, not consistent with sediments. And the serpentinite fractionation line would kind of come up here, so we could explain some of the lower ones, but some of these really highly fractionated ones, probably not. And what's nice is just recently, I don't have the reference on here, sorry. There's a recent paper that analyzed altered oceanic crust, natural samples, Amphibolite essentially, and showed that, nicely they look very similar to the high mu mantle. And so while we haven't done the experiments yet on amphibole, our suspicion is that when we do it, we'll see that it'll have a higher fractionation than antigerite for the heavy noble gases. So this is serpentinite, this is amphibole kind of in our model. And so we can now separate different mantle sources based on where they're getting their volatiles from. And basically the morb and many of the kind of EM1, EM2 are getting their noble gases from serpentinite, whereas the high mu source is getting it from amphibolite. And what's exciting about that is we can then, if we can distinguish those, we can then start to look at other volatiles. I just picked out this paper, a recent paper by Page in 2018, looking at chlorine, boron, and nitrogen in sediment crust serpentinite, the same exact things we're looking at, and saying the proportions of those volatiles in the different layers. So nitrogen mostly in the sediment, whereas chlorine is mostly in the crust. And we can combine, if we can use the noble gas isotopes to say, okay, well, serpentinite is the predominant source in morb, well, that should bring along with it, let's say, a lot of boron, but not a lot of nitrogen and chlorine. Whereas in this high mu source, which has a lot of crust, it should bring a lot of chlorine and boron in it. And hopefully we can do this with water and CO2 as well, if we can kind of distinguish them with the noble gases. All right. Ooh, that was fast. Conclusions, noble gases are recycled at subduction zones. Probably also in pores and grain boundaries. Even our cleanest analyses probably still have some pores in them. And the persistence of pores, how deep into the mantle can you subduct a fluid inclusion is kind of an interesting question. Most of the noble gases are released in subduction zones, so another interesting avenue that we want to explore is looking at noble gases coming out of the forearc, out of arc volcanoes, to see if it matches what we expect from our models. And then, OIB sources are heterogeneous in noble gas ratios, and we think we can use that to link it to the mineralogy of the slab and where those volatiles are come from. Kind of questions we're pursuing, particularly this one. The minerals I'm talking about, serpentinite or serpentine, serpentinite as a rock, amphibole, are not going to make it all the way into the deep mantle. They're going to break down by 400, 500 kilometers, even in the coldest slabs, to get them into the source. If the source of plumes, if those are at the core mantle boundaries, they're going to have to transfer that gas to some mineral or a fluid inclusion or a grain boundary that's going to be able to hold on to those and not fractionate them. Because if that mineral that they transfer it to then fractionates them, they wouldn't look so much like serpentinite as we see. So kind of the next steps are to take some of these noble gas juiced serpentinites that Jack has produced and subject them to much higher pressures, have this serpentine break down, and look what the residues of that look like. And then, as I was talking about, how can we use noble gases to trace major volatiles like water and CO2? Can we see correlations between noble gases and these volatiles? And that's kind of work in progress. That's it.
Okay, thanks, Steve. We have plenty of time for questions, which is great. Can run me ragged.
All right, gotta wait for the microphone.
So, as I understood it, you rejected the recycling or very efficient recycling of noble gases because Rita and people are seeing this some sort of heterogeneity in the noble gases. Is that correct?
Yeah, so we see that in krypton and xenon, the mantle is not completely overprinted.
So, I guess it struck me then you showed the lead and the other systems. We know pretty much all that sediment or material is going into the mantle, but you still see heterogeneity because it's not being well mixed. Couldn't that be the explanation for the noble gases too?
Yeah, it's a good point. Could you explain? Maybe. I'd have to think about that one. Maybe. Yeah, I mean, the thing with noble gases like the xenon is because you have 9 isotopes, like what Rita did was use 5 isotopes to work on a 4-component system, all within, the source of one mantle source for 5 different places. And I'd have to go back and look and see how much heterogeneity she saw in the samples. But the problem with noble gases at this point is there's just not enough sample analysis. What you'd really want to tease that apart would be samples that you have strontium, neodymium, lead, and all the heavy noble gases analyzed. And we looked at that, and there's just so few samples where you have all of those analyzed together, we couldn't really see any systematics between the stable isotopes in high mu, EM1, and the traditional lithophile heavy isotopes.
So just to look at your last few questions about the transport of the deeper mantle, actually Colleen worked on this Bridgemanite here, still our papers on that.
Yeah.
But anyway, my question is, like even you're talking about the 1% or small fraction of them, is that consistent with how after your dehydrations, where they're going? Have you looked at, you qualitatively say it's 90%, 99% of these. Is that based on some kind of petition, or you just?
It's just based on mass. It says what's the maximum amount of krypton and xenon I can subduct and not completely overprint the mantle. Because we know that it's not completely overprinted. Now, maybe if it's heterogeneous and it's not well mixed, maybe you could still subduct more than that. But assuming that it's well mixed, you can put a limit on how much you could put down, and that's far, far less than either the natural samples or the experiment suggests is actually going down to begin with. And so based on that, we say most of it has to come off.
Yeah, but even if you know the petition there and the mass balance there, you still have the question of how to transport to the much deeper, right? And
yeah,
because what
exactly.
is, dehydration is pretty low pressure relatively.
That's right.
If you look at the whole mantle convections and what is really the mechanism to bring them down.
That's right. So that, we could imagine things like as you're dehydrating it, whenever I've looked at serpentinization, metamorphic reactions, they're all very heterogeneous, and even in the most altered rocks, you can, in a sea of serpentine and apriditite, you can find little nuggets of unaltered material, kind of almost inexplicably. This is like Henry Dick's career is kind of based on this, that you can look at some highly serpentinized rock and still find some mantle left. So maybe if that's a kind of an image to hold on to, that all you need is a few of those unaltered nuggets to hold on to noble gases. The lower mantle, it looks like more and more experimental studies showing that lower mantle minerals can have very high noble gas concentrations. The question is kind of I think the middle part. When amphibole and serpentine break down, it's shallow. What's the mineral that could hold on to it long enough to get it to the lower mantle? I think once it gets to the lower mantle, I think those phases could hold on to noble gases. I think the experiments suggest that.
Yeah. So that's exactly my question. Is
Yeah.
actually
Yeah, exactly. And that's right. And so then there's transition zone minerals that hold on to a lot of water. Can they hold on to a lot of noble gases? And even then, I think the amphibole and antigerite in most slabs, they're not always going to break down before that. And so how do you bridge that gap, or is it only the cold slabs that are bringing it? And so one of our collaborators is Andy Smye, who's doing modeling of fluid loss. And we had a paper talking about the difference between cold and hot slabs and how they lose their noble gases. And so potentially it might only be the cold ones that allow the minerals to be stable deep enough to then transfer the noble gases deep. But we don't know that.
I don't remember my mineralogy ring structures.
I haven't looked at it. I've been so focused on it, I haven't looked at what their structures are. I don't know if we have a mineral. And it doesn't necessarily have to be a 6-member ring. It could even be like a 4-member ring that could hold anything that's an highly anisotropic site, at least by what our guess is for why they're dissolving so much. Any anisotropic site would be a good place for noble gases.
Other questions? Pass it right over.
I noticed in your experiments that you mix several noble gases in the vapor at once. And I was wondering if you had to worry about non-ideality and how you might model that, or whether the noble gases are simple enough.
Yeah, I mean, one of the nice things about this problem, you saw the range, 2 orders of magnitude variation in the analyses. So whenever we get that down to half an order of magnitude, we might need to worry about the non-ideality. So it almost assuredly is playing a role, but at so much smaller than our other errors. Like even just the errors in analyzing the size of the pit are probably going to overwhelm those. But for sure, there's probably some non-idealities in the gas, but we just assume ideal for now.
More questions?
Can you comment on the sort of state of the art, how noble gases? What I mean by that is have some mineral sticks in this ring.
Yep.
So what threshold could
Yeah. Noble gases, the concentrations in mantle rocks and basalts are very low. Parts per billion, parts per trillion concentration. So just from a concentration point of view, they're trace and ultra trace elements in most samples. If somehow you got them concentrated enough, and we do have kind of weird examples like gas wells and stuff, potentially, if you could get them high enough in concentration, they could stabilize them. I've heard just word of mouth people, and diamond anvil people here, that when they use different noble gases as their pressure medium, like the minerals can get stiffer than if they're not stuffed with noble gases. And so I think in that sense, if you had some mineral that had big ring structure, some clathrate, and you stuffed it with noble gases in some kind of simplistic physical view, you would prop those open until you would assume they would go to higher pressures. As far as the systems, I'm talking about the mantle and stuff, probably the concentrations are so low that not. There was I think Andy Jeffcoat and one of his students wrote a paper about solid noble gases in the core. So they did some experiments at room temperature showing that you could get solid xenon in the compositions. As soon as you heat those up, as far as I understand, they go away. So.
Okay, any more questions for Steve? Did you?
Oh, I was just going to ask any quantitative work on the brain.
Yeah, so it's one of those things we totally want to understand. In fact, it's what got me into atom probe. I was telling Mike about the atom probe, looking for noble gases on grain boundaries. Difficult right now with the laser. For the concentrations we're talking about, we're using like 200 micron spots, and you really need to get down to nanometers to look at grain boundaries. So we're not going to be able to do it with the analytical methods we have now. We've got some really great results from the atom probe looking at grain boundaries, calcium, aluminum, those kind of things. We did stick one of our serpentinites on the atom probe and didn't see any noble gases. So stay tuned. But absolutely, it's an important problem. We need the tool to be able to analyze them.